basically the next topic that motivates our next topic, which is we need to understand how we know that the individual elements, namely the resistors and transistors etc. are noisy. We need to understand when we put all these elements together, what happens to the output noise of a network. Okay. So, that is the topic that we will study next. Once we study noise, we will be in a position to come back to filters for a brief while and look at what the lowest, signal you can put into the filter will be in order to achieve a certain accepted signal to noise ratio at the output of the filter. So, all right. How many of you have looked at noise, have studied noise in earlier, which course? Okay. And how many of you have looked at, have been introduced to noise from a communication class point of view? 1, 2, okay. The BTechs have not seen noise at all. Okay. So, for those of you who have seen it in a communication class, right, we are not going to go into long theorem proof type results here. Our aim is, given a circuit, can I predict how much noise there is at its output and what the characteristics of that noise are. Okay. And again the idea is to work with practical circuits and be able to understand how to calculate noise, what to do to make to get better noise performance and that sort of thing. So, to get to this stage in communications, you would go through several classes of what a random process is, what ergodicity is, and what autocorrelation is, and then Wiener-Kirchhoff theorem and all that stuff. Okay, it's before you come to the calculations that we do, right? We are going to skip all that, right? And all that I am interested in this course is to give you a minimum bare bones tool set needed to be able to make useful noise calculations in circuits. All right. So, first I am going to mention some facts of life. There is nothing we can do about these things. All right. So, it turns out that if you had a resistor in thermal equilibrium with its surroundings with an absolute temperature T, it turns out that if you put a fictitious voltmeter across the resistor, right, it turns out that the voltage is not, you would ideally think that the voltage should be 0, right, no current is flowing through the resistor after all. So, you would think the voltage is 0, but it turns out that you will see a very, you will see a random waveform. It is almost impossible for me to draw a random waveform, all right. Okay. So, but you will see some random waveform. Okay. Without knowing anything else, what comment can we make about the mean of this random waveform? 0. Why? Why is it? Why should be? How did you kind of say 0 all in unison? I can't hear you. Power? What conservation? Where? Well, there is a voltage, so there is definitely power. Yeah, well, the easiest way to understand this is if the average was not 0, then we would be able to, there is no need for us to sit here, we could go be making power and then selling it, correct? Okay. So, it sounds too good to be true, and remember in life anything that sounds too good to be true is always too good to be true, right? And therefore, the average better be 0, no matter what else is true, the average better be 0. So, first fact of life, the voltage across the resistor Vn of t on average is 0. All right. The next fact of life is Vn of t. The next fact of life is that if you take this Vn of t, you recorded that Vn of t, right, pass this through a band pass filter, an ideal brick wall band pass filter centered at a frequency f, right, and has a bandwidth of a small bandwidth delta f, right. What do you think the band pass filter will do? This is an ideal band pass filter, perfect brick wall with a bandwidth of delta f and centered at f. What will the band pass filter do? It will remove all frequency. I mean, this is a random waveform, this is some waveform. So, evidently it has some spectrum, correct. You take this waveform and then pass this through a band pass filter. The band pass filter is only going to pick up those components which are centered at f and in a neighborhood of delta f around f. Okay. So, if you look at this waveform on a scope, what do you think this will look like? It will look like it can't look like a sine wave of f of frequency f. I mean, if you had to get it can't be a sine wave with frequency f, because if the output is a sine wave, pure sine wave, then this is a linear time invariant filter. So, the input must also be a sine wave, right, but the input is kind of randomly varying. So, what does it because it is a band pass filter, the output will look like a sinusoid, but it is because it is being driven by a random input, the magnitude and phase of that sinusoid, the amplitude and phase of the sinusoid will keep varying. So, you will basically see a sinusoid like waveform whose amplitude and phase are varying. Alright. So, you can measure the mean square value of this waveform. This is a waveform, it is a free country. So, nothing is preventing me from measuring the mean square value of this waveform, right. And if you so make the measurement, it turns out that mean square value will be 4 kTr times delta f. Again, this is what do you call a fact of life, okay. And those of you who are interested in figuring out why this is so, feel free to go, and this has got to do with quantum mechanics and black body radiation and all that fun stuff, right. Okay. So, what is the kind of strange about this formula? I mean, do you find something strange at all? Oh, by the way, 4 is 4, k is Boltzmann's constant, T is absolute temperature, R of course is the resistance value, and delta f is the bandwidth of the filter. So, what do you find as somewhat puzzling about this? It does not have f at all. So, basically this is telling you that no matter where the center frequency of the band pass filter is, the output mean square noise always happens to be 4 kTr times delta f, alright. So, okay. So, therefore, what we now define what is called the noise voltage spectral density And this is, those of you who have not done noise before, there is no need to get intimidated, right. Okay. All that this is saying is that if I take this noise source, pass it, remember this noise voltage spectral density is a function of f, the frequency at which you are making the measurement, right. This is basically saying mean square value of the waveform that appears when you take Vn of t, pass it through a band pass filter of bandwidth delta f and a center frequency f, and find the mean square value here, right, and divide this by, well, if I make the filter bandwidth narrower, what would you expect for the mean square value at the output? What do you expect? If I make delta f 0, what do you expect at the output? You get nothing, correct? So, clearly the mean square value must be dependent on the bandwidth of the band pass filter. So, the mean square value divided by delta f, okay, is some measure of how much power there is in that waveform at that frequency, right. So, this is what is called the mean square value, so the mean square value divided by delta f is basically this is the voltage noise spectral density as a function of f. In English, all that it means is that if you take a voltage a noise voltage with this spectral density, you pass it through a band pass filter centered at f and a bandwidth delta f, you should expect that the mean square value of the voltage at the output of the band pass filter is simply SV of f times delta f. That is all that there is to it. Okay. Now, so now that we have learned some jargon, let us try to apply it. So, what comment can we make about the noise voltage spectral density of a resistor? Regardless of where you put the band pass filter, we seem to be measuring a mean square value of 4 kTr times delta f, right. So, this basically is 4 kTr, and what will be the what are the dimensions of this? What are the units of this? Volt square per hertz, right. Remember that K is, what is Boltzmann's constant? 1.38 into 10 power minus 23, right, and units joules per Kelvin, all right. Is this at room temperature or at some high temperature? Huh? It is a constant, right. A constant is supposed to be constant regardless of temperature, right. That is why it is called constant. All right. So, to put some numbers so that you get a feel for this, it turns out that if you put R equal to 1 K, what comment can you make about SV of f? Please do the math. Yes. 16 into 18 volt square per hertz, right, and this is often also expressed, the square root of this is also expressed in what is called nanovolts per, volts per root hertz. So, this as you can see is 4 into 10 power 9 volts per root hertz. Okay. So, a quick number to remember is that a 1 kilo ohm resistor has a noise voltage spectral density of 4 nanovolt per root hertz. Okay. So, since we are still in early stages, let us kind of see how to make some calculations. So, let us say I take the voltage waveform across a 1 kilo ohm resistor, and I have a low pass filter of 1 megahertz bandwidth. How much, what is the mean square value of the voltage that you see there? How do we do the math? We know that the spectral density is 4 nanovolts per root hertz. The bandwidth is the RMS value at the output will be simply 4 nanovolt per root hertz times 10 power 3, right, which is 4 micro. So, the RMS noise of a 1 kilo ohm resistor in a 1 megahertz bandwidth is 4 microvolts, right. Okay, so this basically prompts the next question. If I make it, if I make the megahertz a gigahertz, what will happen? You get multiplied by 30, right. If I make the gigahertz a terahertz, what happens? Pardon? 4? Yeah. So, if I make the terahertz, 10 billion terahertz, what will happen? If I make it infinity, what will happen? It will be, I mean, the formula is telling us that it will be infinite, correct. So, what is your comment on that? What do you think? I mean, I do not have to measure it, right. I mean, this is just telling you that if I do not have the filter at all, no, I do not have a filter at all, I just have a resistor, that is all. It is telling me, this math is telling me that the RMS value can go to infinity, right. That basically means that air around it should have broken down, and basically we should be seeing sparks everywhere. That clearly does not happen. So, there must be something wrong with this, right. So, that is what is called the ultraviolet catastrophe, and so this all, as I said, all comes back eventually to black body radiation, and I do not know if you still remember your high school physics, but this h nu and by e to the h nu by kt minus 1 and so on. I do not know if you remember black body radiation spectrum, right. It goes up and then it kind of eventually falls off, but it turns out that as far as circuits are concerned, we are always working with frequencies which are at best few tens of gigahertz, and up to those frequencies it is as good as being constant, right. At ultraviolet frequencies, obviously the spectral density is not constant, and beyond that it actually falls off. So, the integral is actually finite. So, do not go right away and then start open a startup saying we will generate energy, right, by using resistors. Okay. All right.